Hey everyone, Mr. Fritz here. We are going to talk about probability. That is, what are the odds of rolling a 1 on a six-sided die? What are the odds or likelihood of flipping a head on a coin toss? Or what is the chance of me having a sock in my shirt pocket right now? We'll talk about that. And in fact, if you were wondering, there's a 100% chance that there's a sock in my pocket. So let's talk about some other probability matters right now. Let's dive into it. What is probability? Probability is, the field of probability theory is what mathematicians use to describe the chance or likelihood of an event happening. We assign every event to a number between 0 and 1, kind of like a percentage. It's including 0 and 1. We call this number a probability. So you can have a probability of 0.2. You could also call it 20%, or 2 out of 10, or 1 out of 5. This has all kinds of applications. In probability theory, we can apply this to physical and biological, sciences, economics, politics, sports, life insurance, quality control, production planning, and a host of other areas. Probability is the math that drives the world, really. So, you see them show up in casinos, in life insurance tables. This is how people decide how much insurance you should pay. You have probability talking about the NBA Finals or the NBA playoffs. You have the Punnett Square, a classic favorite. This is all based upon probability. And in general, we have this 0 to 1 time or span of events and their ability or their likeliness of occurring. We said 0 is an impossible event, 1 is a certain event, 50-50 is an even chance like a coin toss. And then you basically have the spectrum of unlikely to likely events. So let's talk first about the difference between theoretical and experimental probability. Those are actually two different things. Theoretical, we'd say, has no observation to it. This is just in theory. We haven't actually tested anything out. This is just what the probability should be without any sort of observation. And then experimental would be what happens after observation. So for example, I have this six-sided die. I can come up with the theoretical probability of rolling a 6 before I've actually even thrown the die to see what the outcome is. Or you can think of flipping a coin. The probability of flipping heads is 0.5 or 50% or 1/2. And we know this since there is an equal chance of each outcome, so that there's an intuitiveness to that 50-50-ness of it all. If I wanted to actually test this theoretical probability, I could actually flip that coin. I could flip it 100 times, and let's say 41 times its heads and 59 times its tails. We would say that the relative frequencies or the experimental probabilities are given as 0.1 for heads, 0.59 for tails. And we can use this probability notation. The probability of heads is 41. The probability of tails is 0.59. In some scenarios, we're not actually able to determine the theoretical probability of something, and we need experimental probability to give us a sense of how likely something will happen. So take, for example, this experiment, if you will, where a bunch of 145 paper clips were dropped onto a 6x6 squared paper. So a whole bunch of paper clips thrown on a piece of paper, and we want to figure out what the experimental probability is of a paper clip falling inside of the squares or on a grid line. And really, there's no simple way to come up with this theoretically. And so sometimes the best way to actually determine that probability is just by doing it a bunch of times and seeing about what the chances come out to be. So what we can do here is we want to find the probability of a paperclip falling inside the square and on a line. And so what we need is we need the total number of paper clips. This is my total number of experiments or trials. And then we need the amount that were successful or matching with the outcome that we're looking for. So if we want to find the experimental probability of being inside the square, we're going to take a look at the number that fell inside the square, which is 113. That's going to equal 113. And we're going to divide that by the total number of trials, or in this case, the total number of paper clips, which is 145. And we want to take that out to 2 decimal places. So let's punch that into the calculator. 113 divided by 145. And that's going to equal 2 decimal places, round this up to 0.78. And then if I want to do the same thing by calculating the experimental probability of falling on a line, Just like before, I'm going to take my number of occurrences that fit the restriction, so 32 of these are success falling on the line, divided by the total number of paper clips, which is still 145. And that's going to equal approximately 32 divided by 145 is 0.22, 0.22. So these are the experimental probabilities that these things will happen. And the idea with these experimental probabilities is that if I were to throw another paper clip, hopefully it'll follow these trends, that I have about a 3/4 chance of it falling inside of the square and a little less than a 1/4 chance of it falling on the line. So this is to help us infer what would happen if we were to do this again. So why don't you try this example? Here we have a table that charts the length of a commercial versus the number of times it happens. Read through the question, pause the video, give this one a shot, and see how it goes. All right, and here are my 3 solutions. The experimental probability of there being a commercial between 20 and 39 seconds is given by A. The answer for B is for B. The answer for C is for C. The only thing that you really need to think about here is if I want between 20 and 59 seconds, I have to include all of the data from these 2 rows. So that's where I'm getting the 38 plus 19 out of 78. Notice that 78 is always the total frequency of all of these different scenarios.